Thank you very much for introduction. Today I'll talk about this title, from Yukawa's Meson theory to quarks and gluon. And first I will explain what did the Yukawa Hideki do in this theory. So let's consider what Yukawa considered at his time. And the question is, what is the nuclear force at that time? So as you know, atom is composed of nucleus and electron. And the nucleus, as later people found, it's made from proton and neutrons. Proton was discovered in 1918, and it's positively charged. And neutron, it's a neutral particle, and was discovered 1932. Yeah, you can see the size. It's 10 to the minus 8, and it's 10 to the minus 12 centimeter. It's 10 to the fourth smaller than the size of the atoms. And the question is, what bind the nucleus? Nucleons. Nucleon is the name of proton and neutron, and inside the nucleus. And at that time, people only know two forces. One is gravity, Newton's gravity. It's too weak to bind the nucleus. And the other is the Coulomb force. But Coulomb force cannot create attraction. For example, proton and proton, since both are positively charged, force is repulsive. And also, neutron doesn't have charge, so no force between proton and neutron or neutron and neutron. Clearly, at that time, people realized we need new forces, and people call that is a nuclear force. And even though we don't know what was the nuclear force at that time, people speculate the property of the nuclear force. One is that nuclear force must be stronger than Coulomb force, because proton and proton has a repulsion, so nuclear force must be stronger than such a repulsion. The other is, since the macroscopic scales, we don't know, we can't see the effect of the nuclear force. Nuclear force must be short range. It's the size of the nucleus. That is 10 to the minus 12 or maybe 11 centimeter. And then Yukawa proposed his theory, so-called Yukawa's Meson theory, 1935. And he proposed the theory which is as follows. Force between nucleon is mediated by an exchange of virtual particles. And also he guessed the mass of that virtual particle from the range of the interactions. So interaction range is usually proportional to 1 over mass. Therefore, from the size of the nucleus, 10 to the minus 12 centimeter, he guessed that mass is between mass of the electron and the mass of the nucleon. Therefore, people call it meson. Intermediate mass means mesons. And later, people called it pi mesons. And actually, at that time, people know force can be mediated by exchange of the particle. So one example is the Coulomb force. Coulomb force is explained by exchange of the photon, the light. And like this figures, or maybe I forgot, like these figures. But photon case is mass of the photon is 0. Therefore, interaction range is kind of infinite. However, nuclear force is, as Yukawa proposed, it's exchange of pion like this. And the interaction range is finite because the mass of the pion is non-zero. And our particle physics like this diagram, it's called Feynman diagram. And the proton and neutron exchange pion and interact with each other. And later, 1947, pi meson was discovered. 2 years later, he got Nobel Prize, 1949, in physics. It's, as you know, it's first first Japanese Nobel Prize. And this year's 70 years anniversary of the Yukawa's Nobel Prize. And because of his Nobel Prize, the Kyoto University established institute, so-called Research Institute for Fundamental Physics, 1953. This is our institute. That is our building, so-called Yukawa Hall, and this is Yukawa's statue. And this is some photo in front of this door, and this is Professor Yukawa, and this is Professor Tomonaga. Later, he also got Nobel Prize. And we changed the name in 1990 from Research Institute to Yukawa Institute for Theoretical Physics. So we now call YITP. It's our logo. And different color represent different season in Kyoto. And also we have, next to this building, we have another building, so-called research building, which was built 1995. And last year was 65 years anniversary of our institute from 1953. And I would like to explain the more detail about Yukawa's Meson theory. In that case, I said nuclear force, but instead of force, we usually use called potential. And I would like to explain what is the potential first. And in the classical mechanics, let's consider particle with mass m, and xt is some coordinate at time t. And the famous law is so-called energy conservation. So total energy is conserved. And usually total energy can be written in kinetic energy, which is momentum squared divided by 2m. Momentum is mass times velocity. Velocity is the first derivative of the coordinate, and potential energy. So since it is conserved, potential energy is something like this. And if you put particle here, it's going down and maybe going up and going down or something like that. And if so, total energy, if total energy is here, they can only moving around here or moving around here. Yeah. And the good things for the potential is, as you can see this figure, slope gives the forces, and which can be seen from the energy conservation. So energy conservation means energy is independent of time. So you can take time derivative. And for kinetic energy, we get this. And from the potential divided by x, and also x divided by dt. So from that must be 0 because the energy is conserved. From this equation, we can get derivative of time derivative of the momentum to equal to minus x derivative of the potential. And we can regard it, this is force. This is nothing but Newton's third law because P is m times v. So P derivative is ma. So F equal ma is Newton's law. And so in case of the gravity or Coulomb force, force is 1 over x squared, and the potential is 1 over x. And Yukawa's nuclear force can be written in this form. But later, from the experiment, now we have the more complicated structure of the nuclear potential after Yukawa. That is a current understanding of the nuclear potential. And vertical axis is a distance between two nucleons. And this is a potential energy in unit of MeV. MeV is 10 to the 6 electron volt. Electron volt is this in Joule unit. And distance is femtometer. Femtometer is 10 to the minus 13 centimeter. And the long distance at about 2 femtometer, and that part can be explained Yukawa's Meson theory. So one Meson exchange forces, but intermediate distance attraction becomes stronger. As you can see from this figure, ball rolling down in this. That means distance between two nucleons becomes smaller. That means attraction. And that part is a little bit stronger than Yukawa's theory. And Taketani, also Japanese, proposed that can be explained by exchange of two pions, or maybe other mesons rather than pions. But that attraction become into repulsion. You see, now if you put ball here, it's rolling down this direction. That means distance become larger. That means repulsion. That part was predicted by Jastrow. He called this part is repulsive core. Core means two nucleons cannot become closer at this point, like 0.6 pentameter. And this repulsive core is very important. And first of all, it explains the stability of the matter. If there is no repulsive core, nucleus cannot keep their size. They become very dense objects like this. And that is very important to stabilize the matters, or stabilize us. And also, it may explain the explosion of the type 2 supernova. At the very end of the star life, a gravitational collapse of the star started, and it becomes smaller and smaller. But however, at that some point, because of the repulsive core, it's bounds back. Then it starts explosion of the supernova. Also maybe sustain the neutron star, etc. And now, to understand repulsive core, Yukawa's Meson theory cannot explain this structure. And to explain the repulsive core, we have to understand the internal structure of the nucleons. That is my next topic. And that is that is internal structure of the nucleons. And after the Yukawa, more than several hundred of hadrons. Hadron is proton or neutron or meson and others, has been found in experiment. Therefore, hadrons are no more elementary particles. But Yukawa time, only proton, neutron, and electron exist, so he thought that is elementary. But now it's not elementary. And the hadron are made of more fundamental object named quarks. And the proton or neutron is called baryons. It consists of 3 quarks. And the proton case is up quark, down quark, or neutron is up, down. And the meson is made of quark and antiquark, up quark and anti-down quark, etc. And there is a theory so-called quantum chromodynamics, we call QCD. It is a fundamental theory of quarks and gluons, and which was proposed by Nambu and maybe other people in 1965. And the quark, first of all, quark interact themselves by exchanging gluons like this. Quarks, and they emit gluons and absorb gluons. It's like electron interact with exchange of photon. And instead of charge, they have so-called color charge, red, black, green. There are 3 kinds of charge. So it's quark, and gluon. And the gluon is something like photon. And important point is gluon interact with themselves like this, 3 gluon or 4 gluons. That property is absent in Coulomb forces. That is specialty of the quantum chromodynamics. And these color charges are all same color charge. And let me explain some important property of quantum chromodynamics. First property is so-called asymptotic freedom. Interaction becomes very weak at short distance. And that was predicted by Gross, Politzer, Wilczek. They got Nobel Prize 2004. And on the other hand, attraction of the between quarks becomes stronger at longer distance. So it's very different. Short distance, force become very weak, but long distance, force become very strong. And these 2 extreme property can be understood by some kind of so-called string model. If, for example, if constant mesons, up quark and down quark, anti-down quark, if in between there are some string. So if they are close enough, there is no effect because the string doesn't affect at all. However, if you try to separate them, they cannot separate longer than string length. So that is kind of picture or model. And this property, first property called, a second property called co-confinement, because that property said no isolated quark can be observed. Actually, so far we cannot observe isolated quarks. And so, and the interesting thing is only color neutral. Neutral means white state can appear in nature. So there is no single quark, there is no two quark. But if you have three, red, green, black can become white, and this state exists, but four quark state doesn't. And Meson is quark and anti-quark. Anti-quark have complementary color, gray, magenta, yellow. Therefore, then Meson can become white. And these only baryon, three quark state and quark anti-quark state can exist in nature. That is so-called quark confinement property. So if we try to, what happens if we try to separate these quark and anti-quark by putting some energy? And if you put energy and try to separate, suddenly string break. And the quark and anti-quark created because you put energy. And this part is white, also charge neutral. And finally, we get UD bar and DD bar. And so instead of isolating quark, we have this process. Pi plus becomes pi plus plus pi zero by putting energy. Then now our task is we can derive this nuclear force from QCD, quantum chromodynamics. That is our task. This is one of the most challenging problems in elementary particle physics or nuclear physics. And actually, Nambu stated in his book, Quark, Frontier in Embedded Particle Physics, so even now, it is impossible to completely describe nuclear forces beginning with the fundamental equation. But since we know that nucleons themselves are not elementary, this is like asking if one can exactly deduce the characteristic of very complicated molecules starting from Schrödinger equation, a practically impossible task. So Yukawa's ages, the nuclear force is very simple, proton and neutron and exchange pion. But in QCD, nuclear force is very complicated because proton is made of three quarks, neutron is made of three quarks, pion is made of quark and antiquark, and exchange gluon a lot, like this. And not only this time, there are many other diagrams. We have to calculate all diagrams. So question is, so we have fundamental degree of freedom is quark and gluons. But we cannot see such a degree of freedom. What we see, physical degree of freedom, is proton, neutron, and pion. It's stable hadron. And we have to understand interaction among stable particles. That is a nuclear force. That is our task. And to attack this problem, we need some other technique, so-called lattice QCD. Lattice QCD is define QCD on the discrete spacetime, like this. And if we define this complicated QCD process can be calculated so-called by Monte Carlo method with supercomputer. And for example, we can calculate proton or neutron mass, or maybe pion mass, or other particle mass using lattice QCD. And in this theory, we have three free parameters. And that is some example result from some Japanese collaboration, sort of PAC-CS collaboration. That is some several particles, and this is mass in terms of GeV. GeV is a 10 to the 9th electron volt. And as I said, we need three parameters. So we fix three parameters using pion and also other meson, K-meson, and omega particle. And the other is prediction. So red one is lattice QCD prediction, and vertical line is experimental value. And as you can see, lattice QCD reproduce experimental data very well. This is just mass. So the mass is only one particle. But we have to consider two particles which interact with each other. So nuclear force from lattice QCD. That is my collaborator, Hatsuta-san and Ishii-san. And we use a supercomputer, so-called Blue Gene L, which was at KK. This is one of the fastest supercomputers in Japan around 2006. And it's 50 times 10 to the 14th floating point operation per second using total system. It consists of 10 racks. And we use this half rack, this machine up 3,000 hours calculation, and try to calculate nuclear force. But brute force calculation doesn't work. We need some idea. And the previous people tried to calculate nuclear force itself, and it's very difficult. And calculate some scattering process and wave function. And we inverse the problem. We first considering the scattering process, its wave function, and from that we deduce the nuclear potential from this wave function. And we try to calculate this in lattice QCD. It's kind of so-called inverse problem. So this is first calculation in lattice QCD. And we did some approximation, neglect quark, anti-quark pair creation. And in nature, pion mass is 140 MeV. But that mass is very difficult in lattice QCD. So we use a little bit heavier pion mass. And that is our result at that time, 2007. And this is our result. As you can see, this is a potential from the experiment. And this line is a prediction from Yukawa theory, as long distance part. And as you can see, qualitative future of NN potential, including repulsive core, are reproduced in our lattice QCD calculation. Maybe skip. Some response or reaction. First is from Franz Blissek. He came to Kyoto in 2007 and gave a speech at Yukawa Tomonaga Symposium. And he explained some things about nuclear force. And just in the last few weeks, Ishioka and Hatsuta reported the first calculation of their nuclear force based on QCD. They do find the hard core. It's a major milestone in our fundamental understanding of the matter. And he also some article in Nature. Also, our paper was selected in the Nature Research Highlight 2007. The achievement is both a computational tour de force and a triumph theory. So conclusion is now, more than 70 years later, Yukawa's Meson theory is understood from more fundamental theory of quark and gluon, QCD. So we now can derive Yukawa potential, nuclear potential from the fundamental theory. Now, in future, our strategy to understand the nature as follows. So we first calculate potential in lattice QCD from QCD and give it to the nuclear physics and calculation and calculate the structure of the matter. And that information can be used to understand property of the neutron star or supernova explosion. Thank you very much.